Hello. Just want to briefly go over here some stuff with section 8-6, testing a claim about a standard deviation or variance. So essentially going to apply hypothesis testing to now testing for standard deviation or a variance. This section can be a little complicated, so I want this to be more of just kind of an introduction to this section. Won't spend too much time on this one. Alright, so key concepts and just include this section introduces methods for testing a claim made about a population standard deviation or population variance. And so these methods use the chi-square distribution, which was first introduced back in section 7-5, when we were making confidence intervals to estimate a standard deviation or variance. Just reminders for some of the notation that will be used in these hypotheses tests. Again, just n stands for the sample size, just a lowercase s will stand for that sample standard deviation. That s squared is what will stand for the sample variance. The Greek letter sigma will stand for the claimed value of the population standard deviation. That's again claimed value, so that's what we'll be testing. And then sigma squared as well be that claims value of the population variance. Now, requirements to do these types of hypotheses tests include, again, simple random sample is what we usually want for just about all confidence intervals and hypotheses tests. Now, what's stricter with this one is the population has to be a normal distribution. So that's much stricter than, say, the hypotheses test for testing means. The test statistic will look just like this, using our chi-square value. Just using that same formula from section 7-5, where the chi-square value is just equal to the degrees of freedom times the sample variance, all divided by the population variance. And a quick note, when you find this value, this doesn't mean to square all this again. This is just saying it's a chi-square value. That's just what you call it. So once you evaluate this, you don't have to square it again. Now, as for p-values and critical values, you can use technology or table A-4 to kind of help get some p-values. We'll focus actually on this section for critical values, just using that table A-4, the chi-square table. Now, you can use this to estimate p-values, but it's a little overly complicated, so we'll focus on just critical values. And then in either case, the degrees of freedom is still just that sample size minus 1. Now, a quick caution. So the chi-square test of this section is not robust against a departure from normality, meaning that the test does not work well if the population has a distribution that is far from normal. So again, just from before saying we need to make sure we have a normal population, not like we did with the hypotheses test for means. Now, just recap about some properties of the chi-square distribution. All the values of the chi-square are non-negative, and the distribution is not symmetric. It's more exponential. Then there's a different distribution for each number of degrees of freedom, similar to that t distribution. And the critical values are found in table A-4, still using n-1 degrees of freedom. So again, that's kind of more that exponential looking shape. And as your degrees of freedom increase, it starts to look a little more normal, but it still has kind of that exponential shape to it. So before we do an example, again, just a quick summary of the hypotheses test steps. First, we want to identify our claim to be tested. Next, we'll identify the alternative if that claim is false. Then step 3, between those two claims, determine which one of them will be our null hypothesis and which one will be our alternative hypothesis. We still want to stick with where the null hypothesis is the one that involves some sort of equality, and then the alternative hypothesis involves some form of non-equality. Step 4, we'll have to choose our significance level, or that alpha level for type 1 error. Then step 5, we'll decide which distribution to use, which in this case will be our chi-square distribution, and we'll use the chi-square test statistic. Step 6 is we'll actually find that test statistic, and then in this case we'll find a critical value, and you can also use confidence intervals for these types of hypotheses tests as well. Step 7, We'll figure out from step 6 either reject the null hypothesis or fail to reject the null hypothesis. Then step 8, restating our decision in context with non-technical terms. So for an example here, listed below are heights in inches for a simple random sample of 10 supermodels. Consider the claim that supermodels have heights that have much less variation than the heights of women in the general population. And we will use a 0.01 significance level, so that's the alpha, to test the claim that supermodels have heights with a standard deviation that is less than 2.6 inches. So it's claiming that this 2.6 inches is like the population standard deviation of heights among all women. And from this sample of 10 supermodel heights, then that sample variance is this 0.7997 and so on here. And that sample standard deviation is this 0.8942 and so on. So now someone checked that we had a simple random sample. We were told that we had a simple random sample, so we're all good there. Now, again, we'll usually be told that we're working with a normal distribution or from a normal population, but just this is a quick way to check using a quantile plot. Don't have to worry too much about this. We'll just give a quick recap. And along this x-axis here are the actual heights of all supermodels, and then the z-scores along the vertical axis here is kind of what the z-scores should be based on how many data values there are. And these points roughly follow a straight line, so it'll be enough to say that it looks like we're working with a normal population. So we can continue with our hypothesis test. So step 1, our claim that we're saying is that the standard deviation is less than 2.6 inches for the supermodels. So we can use the notation where sigma is less than 2.6 inches, since this is our claimed standard deviation, and less than that claimed value. And if the original claim is false, then that would mean that the standard deviation of the supermodels is greater than or equal to 2.6 inches. Now, how we'll put that into the actual hypotheses here is that the null hypothesis, we'll just go ahead and say that sigma is equal to 2.6 inches, since we still want some form of equals in the null hypothesis, and that still satisfies the requirement that it's different than that original claim. And the alternative hypothesis just being that sigma is less than 2.6 inches, so that the supermodel's height's standard deviation is less than 2.6. So the significance level is, again, alpha is 0.01. Then step 5, because the claim is made about standard deviation, we use the chi-square distribution. To find our test statistic, we go and just plug in everything that we have into that chi-square formula. So we'll plug in those degrees of freedom, so just 10 total heights minus 1. And then that sample variance, again, was that 0.7997 number. And then our claimed standard deviation here, that was the 2.6 squared. So once we would evaluate all that, we should find that our test statistic is a chi-square score of 0.852 with 9 degrees of freedom, which you can also find from that chi-square table. Or we'll refer to the chi-square table and see how this 0.852 compares. So then the critical value of 2.088 is found from table 8-4, and it corresponds to 9 degrees of freedom. And again, the chi-square table, for our purposes, gives us areas to the right. So if we have that significance level of 0.01, that means that the area to the right of this 0.01 is 0.99. So just confirm, I can come into here, and then I have the areas to the right here on the chi-square table where I'm looking at 0.99. So I'm looking in this column to where I've got 9 degrees of freedom. So I can see my critical value is in fact 2.008 or 2.088. And it turns out that actually our test statistic of 0.852 is less than, or in this case more extreme than that critical value of 2.088. So essentially this is falling into the rejection region. And so because the test statistic is in that critical region or rejection region, we reject the null hypothesis. So then there's sufficient evidence to support the claim that supermodels have heights with standard deviation that is less than 2.6 inches. And again, heights of supermodels have much less variation than heights of women in the general population, is how we would say it for step 8. I'm just putting this into non-technical terms in context. In the p-value method, you can do this using other forms of technology, such as a TI-83 or 84. They can find p-values for you that'll end up looking something like this. But for our purposes, what will be best is using the critical value method or the traditional method, and just figuring out which critical values will mark where our rejection region starts, and then see if our test statistic falls in that rejection region or not. You can do on, so if you were to do the p-value method, you find that the p-value would be very small there, 0.0002897, so which is much smaller than 0.01, so you would still reject the null hypothesis in that case and reach the same conclusion. You can also do this using the confidence interval method, where since the hypothesis test is a left-tailed test using that 0.01 significance level, you would run the test by constructing a 98% confidence interval. And so you can use the same methods from section 7-5 for actually creating that confidence interval. Biggest trick is just finding those two critical values, since for chi-square there's a completely different left critical value and right critical value. Since we have that 0.01, we'd already know the left critical value is 2.088. And to find the right critical value, I would just need to know that on the right tail, there's also an area of 0.01. So then I can look up in the chi-square. So I'm going to be looking on this column here, 0.01, since that's the area to the right. Come down to that same row where I should have 9 degrees of freedom. So my right critical value should be 21.666 here. And then once I would look here where I'm actually setting up the confidence interval, just all according to these formulas here, I'd see that in fact that right critical value is 21.666. Then I'm just kind of plugging everything else into that confidence interval formula for estimating a standard deviation, and comes out that essentially we'd be 98% confident that the true standard deviation of supermodels is between 0.5 inches and 1.7 inches, is standard deviation of their height, that is. And so then based on this interval, we could still support the claim that their standard deviation is less than 2.6 inches. So we would have reached the same conclusion, since the claimed value of 2.6 inches does not fit within that confidence interval. So again, if the claimed value doesn't fit in your confidence interval, reject the null hypothesis. Right? And that's chapter 8.